We saw that in the Joule-Thomson effect, the experiment was carried out in an thermally insulating chamber or sealed tube. By thermally insulating, we mean that the wall which separates the system from the surroundings does not allow any heat flow across it, which means heat cannot flow from the surrounding into the system or the other way. In such case, if a transformation happens, we call that transformation as adiabatic transformation or adiabatic change. Now let us try to understand what will be the pressure volume work associated with an adiabatic change in state. Now as before, let us consider that the system is undergoing some change from an initial state P1 V1 to a final state P2 V2. So using the first law, we can write du is d cross q plus d cross w. Again remember that we are using d for exact differential and d cross for inexact differential, because internal energy U is a state function, whereas heat denoted as Q and work denoted as W are path functions. Now for an adiabatic change in state, d cross q must be equal to 0, as there is no heat flow across the boundary. So we can write using the relationship for du that we developed using the condition when we make a change in constant volume. So we had for du Cv dt plus del u del v t dv, and on the right hand side for d cross w we have the expression for pressure volume work as usual. Now let us consider an ideal gas and also further consider this process is a reversible process. Now we already discussed that for ideal gas del u del Vt, this term is 0. So we have Cv dt is nothing but minus P opposing dV, but for a reversible change, remember the change is carried out by changing the external pressure infinitesimally small amount in each step, which means the transformation is done in a manner such that the system always tries to adjust with the external pressure. So the external pressure is nothing but the pressure of the system itself. So it is P dV, and using ideal gas equation we can write nRT by V dV. Now we can just rearrange by writing Cv bar, where I am dividing the Cv by N by number of moles, which means Cv bar is nothing but the molar heat capacity at constant volume. We are also bringing down the temperature here. On right hand side we have then minus R dV by V. Now we can integrate between the two limits 1 and 2. Now here we have approximated that Cv bar is a constant. It does not depend on temperature. It is an approximation. Now the value of the integrand will be, it's basically integral dx by x. So the integral is nothing but ln t2 by t1 is equal to minus r ln v1 by v2. Now we can use this minus sign. Remember that minus ln a by b is nothing but ln b by a. So we can rewrite r ln V2 by V1. So we got, if we further rearrange, ln T2 by T1 is R divided by Cv bar ln V2 by V1, which is, and the right hand side will be minus R ln V2 by V1. And remember, we can use this minus sign by using the relationship minus ln A by B is nothing but ln B by A. So this relation becomes R ln V1 by V2. So we can further rearrange by writing ln T2 by T1 is nothing but R by Cv bar, in this case it's a molar heat capacity, V1 by V2, or we can actually take it to the power by using the fact A ln B is nothing but ln B to the power A. Now we have to figure out this value of R divided by Cv bar. Since we are using ideal gas, we know that the difference between the molar heat capacities for an ideal gas is nothing but R, the molar gas constant. So we can easily figure out what is R by Cv bar. It is nothing but the ratio of the molar heat capacities minus 1, and this ratio we denote as a symbol gamma. So gamma is the ratio of molar heat capacities Cp by Cv, molar heat capacity at constant pressure divided by molar heat capacity at constant volume. So we can rewrite that ln T2 by T1 is ln V1 by V2 to the power gamma minus 1, or we can get rid of this ln and write T1 V1 to the power gamma minus 1 is nothing but T2 V2 to the power gamma minus 1. So we get a very interesting relationship that T1 V1 to the power gamma minus 1 is constant. Remember, this was very different for an ideal gas. For an ideal gas undergoing isothermal change. So we can actually develop further relation using this relationship which we just got between temperature and volume. We can plug in the ideal gas equation PV equal to nRT and get a relationship between, say, pressure and volume. So if you write T, if we substitute T and write PV by nR, we get PV1 divided by nR, V1 to the power gamma minus 1 is equal to PV2 divided by nR, V2 to the power gamma minus 1. So what we get is P1, this should be P1, V1 to the power gamma minus 1 is P2 V2 to the power gamma minus 1. This gamma minus 1 and V1 gets multiplied to get P1 V1 to the power gamma is equal to P2 V2 to the power gamma. So what we get is P V to the power gamma is constant for an adiabatic change. Similarly, we can get a relationship between pressure and temperature. You can just substitute the V in this equation by nRT divided by P using the ideal gas law, and you can show that then we'll get T to the power gamma, P to the power 1 minus gamma is constant. So these are the relationships for an adiabatic change. Now remember, for an isothermal change, if we go from state 1 to state 2, from pressure P1 V1 to say P2 V2, so the curve looks like this, but compared to that, the pressure volume curve for an adiabatic change will be much steeper because gamma is greater than 1. We'll come back to it why gamma is greater than 1. Now before that, let us try to estimate what is the value of gamma. Now here we estimate the value of gamma. For that we need to know a theorem which is known as equipartition theorem. Now for any mechanical system which has or which is composed of say n particles, the system will have a total 3n independent degrees of freedom. What does it mean? For example, suppose take a monatomic ideal gas or monatomic any gas, say for example any rare gas like helium, neon, argon, they are all monatomic gas. So n in this case is 1 and the total degree of freedom is 3. These 3 are actually the 3 translational motion along x, y and z laboratory axis. So if we call this as x, this as y and this as z, then any particle, in this case a helium atom or neon atom, can move in any arbitrary direction and the velocities can be resolved in these 3 particular direction like Vx, Vy and Vz. So there will be some associated kinetic energy also along these 3 direction, which we can write it as Ex is half m Vx square, and similarly for Ey and Ez, whereas the total energy is divided or written as a sum of Ex plus Ey plus Ez. Now if it is a diatomic molecule, say for example carbon monoxide, so what will happen for that? For that n is equal to 2, so the degrees of freedom will be 3n or 3 into 2 equal to 6. So 3 are as before the translational motion which describes the motion of center of mass of this diatomic molecule. Now what are the other 3 degrees of freedom? Now carbon dioxide can also vibrate. It can stretch the bond and it can compress the bond, do like that. So this vibration is another degree of freedom. So we get 3 translation, 1 vibration, and this carbon dioxide can also rotate. So if you think that the molecule is initially aligned along the y-axis, then it can rotate along z-axis like this. Also it can rotate along x-axis. It can rotate along the x-axis like this. However, if we rotate it along y-axis, there will be no change in moment of inertia because it is already aligned along y. So there are only 2 rotational degrees of freedom. So 3 plus 1 plus 2, these are the total 6 degrees of freedom. In this way we can calculate for any arbitrary system which consists of n particle, and the rule of thumb is if it is a linear molecule, by system usually here you call it we will discuss only the molecular systems. So for a linear molecule I'll have total 3 translational degrees of freedom, and then there will be 2 rotation degrees of freedom, and then there will be 3n minus 5 degrees of vibrational degrees of freedom. If it is a non-linear molecule, for example, if it is something like this, water, so then it can have non-zero moment of inertia for rotation along any three axes. You can easily figure that out, because moment you try to align, you cannot align the entire molecule along a particular direction, because the molecule is now not linear molecule. So you'll have 3 translation, 3 rotation. So 6 degrees of freedom has already been taken into account. So you will be left with 3n minus 6 vibrational degrees of freedom. So this way we can calculate. Now the equipartition theorem tells that for any degree of freedom, if the associated energy is or can be written as a sum of square term, meaning in this case we saw that there are 3 translational motion, and the translational kinetic energy along any direction can be written as, say for example, Ex was written as proportional to Vx square. So if this is the case, then each degree of freedom or each motion for that contributes half kBt amount of energy towards the total internal energy of that molecule, where Kb is the Boltzmann constant defined by the molar gas constant divided by the Avogadro number. Now let us take an example. Suppose we have a monatomic gas, which is say helium or any inert gas. So the total degrees of freedom is only translational degrees of freedom, which is 3, and we know that translational degree of freedom can be written as a sum of 3 kinetic energies, where each kinetic energy along a particular direction in space is proportional to a square term in velocity. So each kinetic energy will be equal to half kBt. So the total energy the molecule possesses will be nothing but half kBt for each degree of freedom, or 3/2 kBt. Now usually instead of for one molecule we write it for 1 mole of molecule, so we again multiply it by Avogadro number so that this Kb becomes R, or the molar gas constant. So for the one energy will be nothing but 3/2 RT for a monatomic gas. So the total degree of freedom was 3. So Cv, or the heat capacity at constant volume, is nothing but del U del T V, which is, if we take the derivative, will be nothing but 3/2 R. So you can see that Cp minus Cv already we know is R, and from that we get Cp is nothing but 3/2 R plus R, which is 5/2 R. So in this case Cp by Cv, which is written as gamma, will be 5/2 R divided by 3/2 R, which is nothing but 5/3. So gamma is always greater than 1. So we can take another example, say for example carbon monoxide. Here the total degrees of freedom, there are 2 particles, so the total degrees of freedom will be 3n, which is 6 in this case. Now 3 goes for translation, and the translational contribution will be 3 into half RT. Now 2 goes for rotation, and for each rotation it will be half RT, and then there is 3n minus 5 because it is linear. So 3n is 6 minus 5 is 1 contribution for the vibration. Now interestingly, for any vibrational motion you have 2 interesting contribution from energies, total energies. One is the potential energy and one is the kinetic energy. Remember, the potential energy for a bond vibration can be written as, if we approximate the vibrations are harmonic, we can use Hooke's law, and the energy will be nothing but half kx square, or the energy is proportional to x square, so a square term. And the kinetic energy, as before, is p square by twice m, where p is the momentum, or half mv square. Usually you do not write m, you use reduced mass, but whatever it is, that is also proportional to velocity square. So each degree of freedom in this case, instead of contributing half RT, will contribute RT. One half RT is coming from the potential energy, and half RT is coming from the kinetic energy. So if you calculate in this way, for carbon monoxide we'll have 3 by 2 RT plus this is RT, or we can just write it as 2 by 2 RT, and this is also RT. We can also write it as 2 by 2 RT just for ease in calculation. So 3 plus 2 plus 2 is 7 by 2 RT. So this is the U, and similarly CV bar will be 7 by 2 R, so that CP becomes 9 by 2 R, and gamma, which is the ratio of Cp by Cv, becomes 9 by 2 R divided by 7 by 2 R, which is 9 by 7. In that way, you can also calculate carbon dioxide, which is a linear molecule, and H2O, which is a nonlinear molecule. Both carbon dioxide and H2O have 3n, which is equivalent to 9 because there are 3 atoms. However, the calculation will be different for the linear and nonlinear molecule. Now, this discussion shows that gamma, or Cp by Cv, or Cp bar by Cv bar, is always greater than 1, which means for an isothermal change, we saw that the curves looked like this because of Boyle's law, and the Boyle's law was P was proportional to 1 over V, inversely proportional to the volume. However, for adiabatic change, you see that the curve will be more steeper because now it follows an equation which is P is proportional to 1 by V to the power gamma, where gamma is greater than 1. So the fall off will be more steeper for an adiabatic case than for an isothermal case, because for the isothermal the equation is P is proportional to 1 over V. For the adiabat, the equation is P is proportional to 1 over V to the power gamma. Now, this is the PVT surface for an isothermal change and an adiabat change. You can see that this is a surface for a real gas. We had discussed it earlier that for isotherm, if this denotes the isotherm, the adiabats are much steeper. Also notice that when an isothermal change is happening, it is isothermal, means the temperature is constant. So we took a slice along this temperature. That's why we got a PV isotherm. However, when the adiabatic change is happening, as it is changing, the system's temperature is also changing. So whatever we discussed, that the system goes from P1 V1 to P2 V2 for an ideal gas or any system as in an isothermal change. For the adiabatic change, what we just showed, that the adiabats are much steeper. The system is going to a different pressure volume, and not only that, it is also going to a different temperature. It is not maintaining its own temperature like the isothermal change. So the temperature drops in this case because it is an expansion. And this is a very crucial observation which we will be using. Now again, in the pressure volume diagram, here it is shown that how an isotherm and an adiabat should be written on a pressure volume diagram. The adiabats are always much steeper. It falls off much steeply as the pressure drops or as the volume increases. Now we'll conclude this part by noting down two particular important issues. One is that whenever we talked about energy, we said it is an internal energy, meaning it is the energy associated with the system due to its internal motion. Now what do you mean by that? Suppose we have a system which is an ideal gas contained in some pressure, some volume, some temperature, and then suppose we move the system with some velocity. So the entire system is now moving, and the system as such will have a kinetic energy. However, this energy is not a part of the internal energy or kinetic energy. The total kinetic energy as a whole is not a part of U or internal energy. So by internal energy we mean when the molecules or the atoms, whichever the system is composed of, they are moving around and they are vibrating, they are rotating. The associated energies those associated energies constitute the internal energy U. So internal energy of course has a kinetic energy and rotation energy and vibrational energy and many other energies, electronic energy, nuclear energy, but that is internal to the system. If the system moves as a whole, its kinetic energy will not be considered as the internal energy. So this distinction has to be kept in mind. Secondly, which is very important, we considered a process where we were changing the internal energy as a function of volume and temperature, and there we got a relationship which we just used, which is Cv dt plus del U del V T dV. Now the question was, this was taken to be 0 for ideal gas. Now this was based on an experiment which was Joule's experiment, and remember that in Joule's experiment, Joule found there was no rise in temperature, delta T was 0. From that he concluded del U del VT is 0. However, later on people carried out much refined experiment where they found that del U del VT is not equal to 0, much like we also discussed that del H del P T is also not equal to 0 for any real gas. Now how can you understand that for ideal gas this should be 0, or for ideal gas energy is a function of temperature only? As long as we are not changing the temperature, remember del U del VT means the temperature is kept constant, the internal energy does not change. Now we'll make an analogy with the particle in a box model. Remember, in a particle in a box, one-dimensional box, the expression for energy is n square h square by 8 ml square, where n is the quantum number, h is the Planck constant, m is the mass of the particle, and L the length of the box, which means energy is proportional to the inverse of length square. So if you change the if you change the length of the box or the volume as such, then the energy levels should also change, which means if I suppose this is the initial energy levels, if I increase the L, the energy levels should come closer together. So that is understandable. Then why do you say that del U del VT is 0? Because as we are changing the volume, the energy levels are coming closer together. Now the fallacy is here, at any point you will have some molecules in the ground state, some number of molecules or some fraction of molecules in the excited state. That will be dictated by a factor which is known as the Boltzmann factor. So if we call that for any level which we denote as I, where suppose I is 1 for this is the first energy level, I is 2 for this is the excited energy level, I is 3 for this. So the associated energy, if I write it as EI by, if the associated energy can be written as EI, where EI is nothing but this expression energy, then we can say the number of molecules in this which are occupying this state will be proportional to that, or the fraction of molecules will be nothing but this e to the power minus e by kBt. Here n is the total number of molecules, and this factor is known as Boltzmann factor. Now the fallacy is here, when I am changing the volume, as long as the temperature is constant, the fallacy can be resolved as this. So the answer why del u del v t is 0 can be answered like this. The total energy of the molecule will be the number of molecules occupying in a state multiplying by the energy of that state and taking a sum over all the energy states, which will be nothing but epsilon I. I'm writing this as first into, instead of Ni, I'll write capital N e to the power minus EI by kBt. Now what is happening, if we keep the temperature constant, then changing the volume changes EI. However, since the temperature is constant, suppose we are increasing the volume, then EI decreases, but then this fraction decreases. At the same time, this EI also decreases. So they will somehow compensate and make the total energy independent of the change of the volume, which means the total energy, which we wrote as U in thermodynamic language, is a function of temperature only. So changing the volume, for example increasing, will actually decrease this value, which means e to the power minus e by kBt will increase. However, EI will also decrease, and then if we take the sum, we can show that the sum will still be a constant, which is independent of the change in volume. So let us summarize what we discussed in this section. So we first started with the mechanical equivalence of work and heat, or equivalence between work and heat, where we showed that if we want to raise the temperature of the system, it is not necessary that we have to supply heat. We can also do some work in the surrounding, and the work can be destroyed to produce heat. And that was experimentally shown by James Joule, where he used the falling of a mass to rotate a paddle system immersed in a liquid that increased the temperature of the liquid water, and hence Joule concluded that the old concept that when heat is exchanged, there is something called caloric, which actually gets transferred between two bodies. He rejected that caloric hypothesis, and he said just by doing mechanical work you can also heat up a system. The second thing is that the concept of energy we discussed, where we discussed for any cyclic process the work done should be equivalent to the heat withdrawn. But in that case we saw that for any cyclic process the system comes back to its initial state. So work destroyed in the surrounding increases the temperature in the surrounding, and since by convention we took that heat flowing from the surrounding into the system is positive, since in this case heat was increased in the surrounding, we took a negative sign, and their difference we found that is always 0 for any cyclic process, which means actually we can define a quantity which is now a state function, because for any cyclic process that quantity is 0, and we called it as internal energy or energy. We just described or discussed why it is better to call it as an internal energy, not the energy. And then we talked about changes at constant volume, which was carried out by Joule in an experiment, and he found that for gases del U del Vt is 0, which is not actually 0 for real gases. For ideal gases it is 0, and we just gave a molecular picture for why it is 0. And then we also considered the changes at constant pressure. There we considered the concept of enthalpy. And just like Joule's experiment, there was another experiment, Joule-Thomson experiment, where we discussed the magnitude or how to quantify the quantity del H del P T. And we saw that it can be connected to something known as Joule-Thomson coefficient. And then we discussed the adiabatic changes, and we discussed that for compared to any isothermal change, the adiabatic changes will be much steeper, because for adiabatic change the pressure volume relations are P v to the power gamma is equal to constant, where gamma is always greater than 1. We took some examples and we showed that why gamma is greater than 1. Thank you.